For this demo, I'd like to create a very simple gesture recognition device, something like a magic wand. I'd like it to recognize very simple gestures, like left to right, up and down, and moving the device in a circle. Feel free to get creative with these gestures, but they should be very simple and take no more than a second to perform each one. There are many ways to collect data. I recommend using the same type of sensor to collect data as what you plan to use for deployment. For example, our Nano has an LSM9DS1 IMU, which contains a 3-axis accelerometer. If you plan to deploy the model to the Nano, then I recommend collecting data with it first. This helps you account for any inconsistencies across different models of sensors. If you attempt to collect data from a different sensor, you may run into situations where the model does not perform as well with a new type of sensor. One way to fix this is to extract features that do not depend on the exact nature of that sensor. For example, the Fourier transform, which we'll talk about in a later lecture, is one good example, as it gives us the frequency components of the input signal rather than using the raw signal itself. Not all feature extraction methods work well for training machine learning models, but some can help you collect data from one type of sensor and deploy it to a board with a different type of sensor. For now, I ask you to stick to using one type of sensor to ensure that your projects will work. If you collect data with your smartphone, make sure you deploy to a similar smartphone. And if you collect data with the Arduino, make sure you deploy to a similar Arduino board. Once you're certain that everything works for the projects in this course, I encourage you to try deploying the model to a different board than what you use to collect data. Playing around with the models and parameters is a great way to get a feel for what works and what does not work in machine learning. You might try collecting data from multiple sources to see if you can train a more robust model and then deploy that model to different hardware to see how it performs. To connect with your phone, head to smartphone.edgeimpulse.com. Make sure the phone is connected and head to Data Acquisition. Let's start with the left to right label. Note that Edge Impulse will collect 10 seconds of data here, so we will perform the motion a bunch of times. Click Start Sampling. Make sure that you're still on the same web page. When it says to start, begin making the motion with the phone. You can vary the motion some, but try to keep the phone in the same position and use the same frequency. Varying how you hold the phone and using a different frequency in your motion may help you create a more robust model, but you will likely lose some accuracy. I recommend sticking to one position and one frequency as much as possible for now, but feel free to play around with different positions and frequencies later. If you scroll down, you can see the raw X, Y, and Z data from the accelerometer that we just collected. If you don't see a repeating pattern like this, I recommend deleting the sample and trying again. Otherwise, you'll be trying to train a model with bad data. Repeat this process until you get about 200 seconds of data for this one class. Because we're collecting about 10 seconds for each sample, you should have about 20 samples when you're done. Once you're done, do the same thing for the up-down class. Edit the label to say up-down. Here, I'm moving the phone in a steady up and down motion. Once again, collect about 200 seconds for this class. If you run into any errors collecting a sample or something doesn't look right in the plot, you can delete the sample and start over. Then let's repeat this collection process for the circular motion. Begin by changing the label to circle and start sampling. I recommend doing clockwise for half the samples and counterclockwise for the other half. This will help create a model that can recognize either of these motions as a circle. At this point, you should have around 600 seconds of data. While we have 3 different motions, we should create one more class for when the board is idle. Change the label to idle and begin the collection process. Here, leave the phone on your desk or simply hold it in your hand for the 10 seconds. Again, repeat this process to collect another 200 seconds of data. When it's all done, you should have around 800 seconds of data, 200 seconds for each label or class. If you are using the Arduino Nano, bring up a command prompt and run the Edge Impulse daemon like we did in the previous lecture. Select the serial port for your board, and you should automatically have it connected to the project, which you can verify in the studio. Go to Data Acquisition, give your label a name, and click Start Sampling. After a moment, you should see the button say Sampling. At this point, you'll want to make the same motion that we did with the smartphone, but using the Arduino board instead. Continue this process until you have collected around 200 seconds of data for each of the 4 classes just like we did in the smartphone example. Note that you should use either the smartphone or the Arduino for this process. I do not recommend mixing data from the two devices at this point. If you want to try both, you should start a new project, one for the smartphone and one for the Arduino. On your own time, I recommend collecting data from both the smartphone and Arduino in one project, but let's keep them separate for now to ensure that everything works. If you want to switch your Arduino board to a different project in the daemon, enter the command edge-impulse-daemon --clean, which will have you log in again and ask you to select a new project for the board. Now that we have our data set, we need to split it into training and test sets. The basic way to do this is to randomly shuffle the data and then divide the data into a training set, a validation set, and a test set. You'll often see 10 to 20% of the data set aside as the test set, another 10 to 20% set aside for validation, and the rest used for training. The training algorithm, something like backpropagation, will use the values found in the training set and the associated labels to update the parameters in the machine learning model. We then use the validation set to test the model's performance, as the model will not have seen the data in this set before. If the model does not perform well with this validation set, we can tweak the hyperparameters, such as the size and shape of the model, number of training steps, and learning rate. We would use the training set again to retrain the model with these new hyperparameters and test its performance again with the validation set. Only once we are happy with the model's performance do we turn to the test set. This test set should be set aside at the beginning and never used until the very end. This final test gives us our performance metrics when we go to report on how good the model is at accomplishing its task. The reason we have separate validation and test sets is because the model will begin to learn some of the characteristics of the validation set every time we update the hyperparameters to make the model perform better on the validation set. The test set, unlike the validation set, will never have been used on the model. If the validation set performs well but the test set performs poorly, it likely means your model has been overfit to the input data, which includes the validation set. We will talk about overfitting in a future lecture. Note that there are other ways of dividing up your dataset, such as with k-folds cross-validation, but we will use the simpler holdout method in this course. Also, note that Edge Impulse will automatically randomly select a validation set from the training set for us during training, but we do need to specify a test set. When you are collecting data, make sure you think about what you're trying to classify and if that data truly represents that class. For example, let's say we are trying to create a model that classifies pictures of dogs, and we feed it a bunch of pictures of poodles as our training data. We then test the model with an image of a Welsh Corgi. Do you think that the model will be able to classify this as a dog or not? And the answer is, it depends. Maybe the model generalizes enough to pick out common features like eyes, a snout, round nose, and so on. However, what you'll likely find is that the model trained on features unique to what we gave it in the training data, such as curly fur and floppy ears. It will have a hard time classifying new images that do not have these features. This is one limitation of machine learning, at least with our current technology. Humans, even toddlers, can see only a poodle, be told it's a dog, and then they can usually generalize to other breeds, such as successfully labeling a corgi as a dog. Most modern machine learning algorithms are terrible at generalizing, and we must take great care to ensure that the data they learn from represents the data we ultimately want them to work with. Just like with my pumpkin project, I did not take care to create a representative dataset, and the model only worked with adult voices, completely missing the voices of my intended user group, which were the children coming to trick or treat. Let's say we use a dataset like this, and let's assume I have thousands of similar images, enough to train a classifier. Also, we'll say that I've got a good representation of all dog breeds. While these are amazing photos of dogs, what problems do you see using this as a training set? There are a number of problems with this set. The first is that they all have dark backgrounds, so a classifier might think any photo with a dark background is a dog. Second, they only contain the faces of the dogs. If you showed the trained classifier a picture of a dog's full body, there's a chance it would miss it. And if you showed it the back of a dog's head, it might also misclassify that image. Finally, these are photos of dogs. While most humans can see a real dog and successfully generalize to a drawing or cartoon dog, our model will likely fail identifying illustrations. The lesson here is to really think about your end application and the training data needed to represent how your model will be used when deployed. There's an old saying in the computer science world, garbage in, garbage out, and it applies here too. If you feed your model bad training data, you will likely get a bad model, even if you have the greatest machine learning model in the world. Now, let's say you're creating a machine learning project that is supposed to let you know when there are dogs in a nearby park. So you collect a large representative data set of empty field images and a large representative data of dogs of various breeds in various outdoor settings. You know that 99% of the time the park will be empty, so you feed the training algorithm a data set that represents that. Nearly 99% of the images are of empty fields, and only a small amount of images are dogs. You then use this data set to train a classifier. You go to test your model, and you find that no matter what kind of image you feed it, it always classifies it as field. If you give it a test set that is 99% field images, your classifier would be right 99% of the time, giving it an accuracy of 99%. If you're measuring performance based on accuracy, this would be amazing, but it would be totally useless for our application. In fact, why use machine learning at all if you just want to label everything as a single class? This is known as a naive classifier, and you will find it happens quite often, especially if you're using an imbalanced data set as shown in this example. We'll talk more about spotting a naive classifier in a later lecture, but how do you think we can fix this? Getting more data will always help. If we don't have access to lots more images, we can balance the data set. That means adjusting the number of samples in each class to be about equal. For our 2-class problem, that might mean a 50-50 split. For 4 classes, aim to get about 25% of samples for each class. While this might not be representative of how often we expect to see the target class, which is a dog in this case, balancing your data set often helps create a better classifier. If you have very few samples of the target class to work with, you may need to use a different type of machine learning model. For example, let's say you are trying to make an email spam detector. You have thousands of regular emails to use for training and only a handful of spam samples. Creating a robust classifier would be difficult for this problem. Since we only have 2 classes and far more samples of non-spam, we may need to turn to a different method for identifying the spam. In this case, we may want to use a form of anomaly detection, which is a special type of classifier. We'll talk about anomaly detection in a later lecture, but know that it is an option for these types of cases. Edge Impulse has given us a way to automatically balance our data set. Right now, everything is in the training set, so head to the dashboard and click on the Rebalance Dataset button. This will automatically split our data set into 80% training data and 20% test data. You can see this by going to Data Acquisition and clicking on the Training Data and Test Data tabs. You should also make sure that your labels are about equally divided. If you've been following along, you should see 4 classes: left, right, up, down, circle, and idle. There should be about 25% of the data in each class in both training and test sets. If you find that you need to move some of the samples from either the training set to the test set or from the test set to the training set, you can filter to find the class name, click on the 3 dots, and then click Move to Test Set, or if you're in the test set, click Move to Training Set. Do this for a few random samples if you need to balance out the training and test sets. I recommend making sure you have enough data before moving on. Without good data, we're not going to get a good classifier.